So, thanks for coming. I'm really excited to be giving this talk. So, I work at Thinkcell. We are the world's leading business presentation software. We are the industry standard for everybody who does PowerPoint for a living. Like we're used by every consultancy company, by almost all executives. They all use our plugin. It seamlessly integrates into PowerPoint and just makes it so much easier to create slides and charts and diagrams. It just saves a lot of time. This is done by reverse engineering Microsoft's code, sort of hacking ourselves into PowerPoint to like seamlessly integrate into it. And like we do everything in C++, we support C++ standardization and everything, and most C++ conferences, as you probably know. So at the core of our product, at our infrastructure code, is the Thinkcell standard library. It's heavily built around ranges. It predates both std ranges and range v3, and like range v3, it was sort of an evolution of boost ranges. But like Flux, we also moved a bit away from iterators internally and instead have cursors. So I'm not sure whether you're familiar with Tristan Brindle's Flux, but the idea is that instead of having an iterator, which remembers both the position and also how to get to the next element, you've got a dumb cursor, which only remembers the position. And if you want to get to the next element or to dereference it, you have to ask the range. Given this cursor, give me the element, give me the next cursor, and so on. However, unlike Flux, which just provides cursors instead of iterators, cursors for us are an implementation detail. So we still provide iterators, but thanks to cursors, we don't have the bloat that happens when you like deeply nested view adapters. We just keep adding stuff into it. It's partially public on there, and I've also given a talk about some of the fundamentals at CppNow 2 years ago. So what this talk is about. This talk is about missing range concepts that we have implemented in our Thinkcell library. And some of them would make a really good fit for the standard library. Our implementation constraints are the cplusplus23 subset implemented by MSVC. But for the purposes of this talk, I will be using cplusplus23 features and cplusplus26 features for convenience. Also for convenience, I will just present everything in the std ranges namespace and use the std ranges names instead of our own. This is just for your understanding, they're mostly equivalent. However, none of this is a promise that any of the stuff I'm talking about will actually gonna make it into the C++ standard library. And even though I am recently the chair for the study group for std ranges at the C++ committee, this is not committee approved stuff. This is just some ideas we have implemented and we would like to see. So the structure of this talk, I've brought 3 problems and a bonus. Problem 1 is about optimizations for better performance. Problem 2 is a metaprogramming for like some compiler magic, and bonus is about some unresolved standard deslowering. So this should really be something for everybody. The conventions, I will be using stdv and stdr for the corresponding namespaces. And then for potentially future ranges and views, I will use the std2v and std2r namespace. So let's begin with the first problem. The first problem is we want to read a file, and we want to normalize all tab characters to 4 spaces. This can be done pretty straightforward using range code. So we've got our read file normalize function, which takes a path. We then read the file, which gives us a range over all the characters. We transform each character. If it's a tab, we return a string consisting of 4 spaces. Otherwise, we return a string, leaving it unchanged. And because those are small strings, they fit in the buffer, so this doesn't do any memory allocation or anything. Now we've got a range of strings, but we want a range of characters, so we join it into a single range, and then we turn that all into a string. And so the read file function simply takes a path and returns some sort of input range, and the magic is in the iterator. So the idea is we like have some fixed size buffer statically allocated on the stack somewhere, and we keep reading it, filling that buffer. So the dereference operator simply gives us the current buffer position, and then as we increment, we check whether we reach the end of the buffer, and if so, we fill it again. And if after filling again, buffer cur is still at the end, this is our EF condition, and we've exhausted the entire file. And this is pretty straightforward code to just read a file in a view. Now the first concept is one that's actually going to make it into cplusplus26, approximately sized ranges. So we're calling toString at the end. And if you're having a sized range, this is quite straightforward. So essentially, the implementation creates a string, reserves the appropriate amount of space, and then copies the stuff in there. So one allocation, and we just mem copy the bytes over, essentially. If you have a forward range, we can still do one allocation. We just don't have the size. So we walk over the range once to compute the distance, get the size, do a single allocation, and fill it back in. However, if you're having an input range, we can't actually do that. Because once we walk over the input range to compute the size, we can no longer walk over it again. We've consumed everything, so we can't actually call reserve. This means that we just call repeatedly pushback, which will then trigger the logarithmic reallocation stuff. And that's a bit unfortunate. It's unfortunate because we are having an input range that isn't sized, right? So read file itself, this could be a sized input range. Like we can get the size of the file from the file system, but it's an input range. We then keep it a sized input range of sized ranges, but when we join it, after joining it, this is no longer sized. Even though the outer range is sized and each inner range is sized, putting it back together isn't sized because it would be the sum of each individual ones, and we don't know how many tab characters we had. So this would be like a loop to compute, so it's not sized. However, we know the approximate size, because let's say most of the time our file does not contain tabs. It only contains spaces, it has been properly formatted. And so we know that join has approximately the same size as the input, because most of the time we didn't change it. Right? And so CppNow adds a new concept to capture that, an approximately sized range. If you're an approximately sized range, you have this reserve hint function. It's a bit unfortunate that the name doesn't reflect the concept, but the idea is the reserve hint gives you the approximate size that you can use for reserve. And so you can reserve the approximate size and copy it over. And so the implementation, it's like an expression equivalent to calling size, or like the reserve hint member function or ADL thing. And then the various views that propagate approximately sizedness in addition to sizeness. So like the views that like don't change the size or like change the now the size, they will just propagate the approximate sizedness. But crucially, join doesn't. Join, even if you have an approximately sized range, join still isn't approximately sized because in general it can't know, right? The size can be arbitrary relation to the input. So it can't do that. So we need some way to tell the code, hey, we're having an approximately sized range of the given size, right? And so the missing thing here is just like some convenience view that grabs an input range and like provides a size, right? So we just construct it from a view and a size, and this is then the size that serves as our reserve hint. And then we can say, hey, so before we call it to a string, we say we know a view, it's approximately sized the same as the input, which is the same as the transform, and then the thing we're wrapping is the joint version, pass that to a string. And this works. If we don't have any spaces, if you don't have any tabs, this will just do one allocation, fill it in nice and smooth. Right? And that's the common case what we're optimizing for. It's just a bit ugly. We have to like put the range in a separate variable because we're using it twice, like once to get the size and once to join it. So a convenient function would be like range adapter closure, where we just say, hey, approximately unchanged size, and then transform it further. So this will sort of query the thing back together. So the implementation wraps some like partially applied range adapter closure, so like the join, like some unapplied range thing. And then when we give it a range, we forward it as an approximately sized view and say, hey, we have the same size as before, but the resulting view is not modified. And that way, we get the desired effect in a very convenient. Now let's talk about something more interesting.
John,
yeah.
Question.
Sure.
If I'm calling to container with a forward range, does the standard specify that the implementation has to compute the size, or is it a QOI issue?
I think it's allowed to. Yeah.
But is it mandated to?
I don't know.
QOI?
I don't know.
Okay.
But it is allowed to, and I would hope so that it will do the thing. Oh, yeah. So this is the, I'm going to ignore the approximately sized for the rest, just for like brevity, because it doesn't really change any of the underlying data. So this is the range pipeline that we're having. We are reading a file, we're transforming it, we're joining. And the imperative code would look like this. So if you just write the entire thing imperatively, you would just keep reading into a buffer, like assuming the buffer is like some array that lives somewhere else, so you get like a span into the buffer. If this is empty, then we're done. Otherwise, we iterate over each character, we transform it as appropriately, iterate over it, and then do something with it. Right? And this would be the imperative code. And of course, the imperative code, like, we can only do like one thing with the dot there. So we'd have to like rewrite it every time we want to do something with the characters. So the range code is superior. The problem is though, the range code like doesn't look like this in the assembly level, right? Because we're having iterators. And so we've got some sort of state machine. And in particular, we're beginning with like a join iterator, which has like the transform iterator over the outer range and then the string iterator over the inner range, because we're joining a range of strings. Then the transform iterator wraps the iterator of the read file, and then the read file has the 2 pointers. The dereference of join just dereferences the current position in the inner range. The dereference of the transform transforms the base range with the function resulting in a string. And then the read file iterator simply dereferences a pointer. And then the increment, so if we call ++ on join, we will call ++ in the string iterator. If this reaches the end of the current range of the current string, then we skip to the next non-empty string. So we've got a loop in the ++ to skip over empty ones. In our case, none of the outer ranges are empty, so this just does one increment. And then we reset the inner position back to the beginning of the next one. The transform one, the ++, that we're calling here when we're calling ++ outer, we're forwarding to ++ base. This just forwards to the read file, which then does something similar to the join, where we like increment the buffer pointer, and if it reaches the end, then we go to a new buffer. Right? And this means that like in the imperative code, we've got some nested loops, and with the iterators, we've got the state machine where the loops are split into read and advance, and then this is like arbitrarily deeply nested, right? Like each of the iterators has its own state machine that are then nested, which means that iterators have some sort of overhead before the optimizer starts, and the optimizer might not be able to see through that and optimize that all out. And that's a bit unfortunate. And it's like really worse for like, for example, join, because like join is logically two nested loops. You iterate over each one of the outer range, and then you iterate over each element, right? It's two nested loops. But instead, we've got the state machine where we've got the loop in the ++ to go to the next one and that sort of thing. Concat concatenates ranges one after the other. This is logically just n loops in sequence. But instead, we've got a complex state machine where we have like a variant of all the iterators, and then they increment the currently active one. And if this reaches the end, then we change the active variant member. And this is like really awkward for the optimizer. And also we've got the famous problem where we do a transform at a filter. This is logically just one loop with an if. But because both the filter ++ and the filter star needs the value after the transform, it applies the predicate twice. Like once to actually get it out of there, and like once to know whether to skip it, the element. And so this is just like semantically less efficient than the other thing. And the optimizer, there isn't like really a lot that the optimizer can do unless it knows that the predicate doesn't have side effects. So why do we have the state machines? And we have the state machines because ranges are pull model, where the range consumer is in control, right? You can write code like this. You get some range, you start iterating of it, you use your value, you skip a value, you use a value twice, you skip over some more value, you use it, and then you just stop. And then the range just sort of lays there, right? The range consumer is in full control over when to get the value, which values to get. It can go forward, it can sometimes go backwards, it can skip values, it's in full control. Right? But this is often unnecessary, because if all you're doing is you're taking a range and you're calling for each, you don't need this flexibility, right? You don't need control, you just give me all the values out of the range, right? So every time you just use a simple loop over a range, you represent the range by a potentially complex state machine, and then you just advance the state machine repeatedly until completion, right? We've got all the state machine, but we don't need the state machine code. This is just overhead. Right? So it's better to express the loop directly using a push model. There, the range producer is in control, and the range just gives the consumer the values, and the consumer can't really do anything. Like it just receives the value in a function object. Right? It just has to process them one at a time as they arrive. But like often, this is enough, right? And so we've got the range-based for loop, and it works by desugaring it into iterators. But we don't really need the desugaring into iterators. We need some sort of push model for that, for most performance. And so what we really want is like the direct customization of the entire loop, right? And Barry and I had a proposal last year, or 2 years ago, where we just say, hey, you can customize the for loop. And essentially what the compiler would do, it would turn the body of the for loop into lambda and pass that lambda to a customization thing on the range, and then you can have the push model. This was unfortunately rejected due to like implementation concerns, although, for example, Go recently added this exact feature. So it is a solution in that space. Barry also wrote a blog post about how to do that using like reflection token injection. You essentially create like a reflection macro that generates the for loop for you. It just has a bit of awkward syntax, but technically that works. What we did at ThinkCell, however, is a library solution. And this is simply adding a new customization point for each while. So for each while iterates over the range and calls the sync for each element while the sync returns true. Right? And this is a push model. So the default implementation simply uses the range-based for loop. So by default, we iterate over the range using the range-based for loop, pass the value to the sync. If the sync returns false, we short circuit, otherwise we continue. Right? And this is sort of enough to model a loop with a break. However, we can customize that for example, transform view. For transform view, we can say, hey, the custom transform view for each while is we call for each while on the base range. And then we don't directly invoke the sync with the value, we invoke the sync with the transformed value. Of our join view, we can just express join view as the two nested loops. We've got a loop over the outer range, and then each element of that is a range which we loop over in turn and pass that to the inner range. And by using the for each while customization point, this then recursively calls the most efficient way to loop over the entire range. Okay? And so, for example, another view where it makes sense is the read file view. We can just express that as getting the buffer. If the buffer is empty, we're done. Otherwise, we're calling for each while over each element of our buffer, passing that to the sync. And this allows us to naturally express the entire loop of a range with one single customization point and not the state machine. And this is really useful. Right? We can directly start using the for each while customization point in various algorithms. Like all the algorithms that are essentially loops, like for each, copy, transform, min, max, count, they can all just use for each while instead of the range-based for loop and get a potentially speed up. Right? If you're doing like a for each of a concat or a copy of a concat, using it via for each while is a lot more efficient than using it via the iterators because you completely avoid the entire state machine. And because it's short-circuiting, we can also use it in the short-circuiting algorithm, like all of, equal, or contains. Right? We can stop at any point by returning false from the sync, so we can implement them in terms of for each while. What we can't do is like do any algorithms that actually require iterators. So like find that returns an iterator, we can't do that using for each while. What we could do is a variant of find that returns an optional t, right? Because we don't have iterators, we only have values. But in our case, we are having S2, so we can use for each while. And so after inlining the first level, so we've got a for each while of a join. And the for each while of a join is simply the for each while of the outer range and then for each while of the inner one. Inlining it further, so the inner range is a string, so we just use the default implementation because that's the most efficient way to iterate over a string, and so we end up with this. So now we are doing a for each while of the base range, which is a transform. So inlining that, we iterate over the base of the transform and simply invoke the function to get the translation, to get the string, and do it with that. And now the base of the base, that's the read file view. So inlining that further, we end up with the while where we read the buffer. If the buffer is empty, then we break. Otherwise, we have the code from before. Right? And this is exactly the imperative code. The only difference is that instead of the dot or dots, we're invoking the sync. Right? So just by doing repeatedly inlining, which is like an optimization compilers are really good at, we end up with the imperative code that we would have written without using ranges. Right? And that's really nice. Like the no state machine, the optimizer has to see it just inlining, and we end up with the performance we want. Now, you might ask, well, why not use coroutines? Right? So we've got the generator, and we can write our generator, where we just write the imperative code, and then we call co-yield. And this is sort of the equivalent thing. Except that coroutines are still state machines. It's now just the compiler generates the state machine, not you. It's still the pull model. They can like pull the values out of the generator, you're not getting it pushed. And then additionally, we have additional coroutine over it in the forms of like heap allocations and stuff. So, but to make this feasible, we really need like better optimization for the generator to like support this sort of push model. Because for like, so generator, this is the one with the nice syntax, but it has the bad performance. And so like for each while is sort of to co-yield what senders receivers are to co-await. A more efficient way to like implement this particular thing. And so this for each while customization point, it's really nice to optimize the ranges. We use that extensively in our library, but of course there are like some more nuances to that. For example, reverse, right? Reverse is logically also a single loop, it just goes backwards. So maybe we want like a customization point to like go in reverse. We actually do that, but that means that everything has to implement two customization points, like one going forward and one going backward. And it's usually the same, it's just you're calling for each while reverse in the implementation instead of the other one. But then you got reverse. Not sure whether that is worth it. When you're calling zip, so the zip iterates over ranges in lockstep. And the way it does that is it has like one iterator of each range, and then it advances them all at the same time. And you can't really do that with for each while. You can't use for each while to iterate over two ranges at the same time. The best you can do is you can use one for each while to sort of drive the loop, and then use iterators for all the other ranges. And so after you pass the values to the sync, you increment all the other iterators. And so like one range drives everything, and the other ones just use iterators. And so if you do that, the question is, which of the ranges is the one using for each while? Well, it should be the one where for each while gives you the most speed up over iterators. So if you've got a concat in there, the concat is the one that should be used for each while, and then the other ones should use iterators. But like, how do you know that? Do you need like some customization point to tell a range how bad it wants to use for each while instead of iterators, and then you pick the one that's like most wants to use that? Like, it's non-trivial. We can't use find with it. Like, we could imagine like a for each iterator while element customization point, which gives you an iterator instead of the element, and then you can use that to get find. Because you just get each iterator and then you just return the iterator of the element that matches. But then you've got additional overhead because you like have to construct the iterator again every time you call the sync, and this might completely neglect all the advantages you have from for each while. So we don't actually have an for each iterator while in our code base. What we do have, however, is generators, and that are not even ranges. Those are simply things that only have for each while. They don't have iterators. And the reason for that is they're like so much more convenient to write. Like, you just have to write a for each while function that passes the sync with the values, and you don't have to start writing an iterator. Like, writing an iterator is non-trivial, a bunch of code. Just writing a for each while function is a lot simpler. And so all of our algorithms and views that don't need iterators, they just work with generators that only have for each while. So you can still use like a filter on something that doesn't have iterators as long as it has for each while. And that's just a nice convenience thing. And of course, the big thing is that like even if we have the for each while customization point and get the optimizations, those optimizations completely ignore the range-based for loop. If you use a plain range-based for loop to consume your range, you don't get any speed up because that one still uses the iterators. And so what we really want ultimately in the end is additionally some language mechanism to forward the range-based for loop to this customization point. But that's like non-trivial. And so in our code base, we've actually banned the range-based for loop. We require everybody to use for each instead, because then you get the optimization. And also, this is the only way to iterate over generators. They don't support the range-based for loop. One convenience thing we additionally have is, so like in the common case, your loop doesn't have a break, and so your sync will always return true. So we make that implicit. Like if the sync returns void, that's an implicit return true. And in fact, it's more of an implicit return true type. Because if we return true type, then we can sort of tweak the implementation and statically detect, hey, is this a sync that requires breaking? And if it isn't, then we just call it unconditionally and we save the additional branch. And then once we reach the end of the code, we like unconditionally never break, so we also return true type, and then we propagate that up appropriately. This is a bunch of annoying code, so it's actually wrapped in a micro. There is a paper in flight by Barry, a control for operator that will just make that possible for you by just using the double question marks there and the sort of short circuits based on some customization thing. It's a really nice paper. It's unfortunately stalled pending for implementation experience. Now, this is the implementation of range to string now that we are from the previous section. So if it's approximately sized, we use the reserve int, and this sort of subsumes sizedness. If it's forward range, we compute the distance. Otherwise, we can't do a reserve, and then we do a copy. But there is an optimization possible for contiguous ranges. If you have a contiguous range, you can just call append. And this will just do the necessary allocations in the string, and then it will just mem-copy the data over, and we don't have to go through pushback, as would be in the case for the copy case. And this is nice because there are a bunch of contiguous ranges, like vectors, arrays, strings, and span. They're all contiguous. However, then we've got ranges that are contiguous, but parts of them are contiguous. They have contiguous chunks, like dec. Dec is a linked list of arrays. So it's not contiguous, but it has chunks that are contiguous. If you concat two vectors, that's not contiguous, it just has chunks that are contiguous. If you have a range of spans and you join that, again, not contiguous, just the chunks. And this is essentially what we're doing in read file. We have a range of spans and we join them. So this is not contiguous, it just has contiguous chunks. And if we have contiguous chunks, we could just mem-copy those over into our strings, right? And so we want to like get them, right? We want like, we have this natural segmentation of ranges into chunks, but how do we express it? How do we express them in a way that makes it usable? And in fact, we already did that. We already expressed the range in a way that exposes the chunking when we implemented for each while. When we call for each while on the join loop, we're calling for each while for each chunk sort of the range. Right? In this case, we've got like each join view, the inner range is one chunk, and we're calling for each while as one call for this entire chunk. Right? if you're having a read file view, we're calling for each while on each contiguous chunk when we call our span. And that means that by just tweaking the for each while customization point a bit, we can give the sync access to this contiguous chunk. And so we define it like so. So if you're calling for each while, first of all, it tries to call s.chunk given the range. So if the sync has a chunk method that accepts this particular kind of range, then we give that to the range, give that to the sync as one thing, right? Otherwise, we use the ADL one, and otherwise we use the default implementation. And crucially, the sync gets to customize first, not the range. So the sync gets to express, hey, I know how to handle this entire range at once, and only then does the range get a chance to optimize the loop, because the loop would still push character by character, element by element. And so what we can do is we provide a string appender sync. The function call operator takes a single character and calls pushback, but we also handle chunks which are contiguous ranges. So if we're having a natural chunk in there that is a contiguous range, we forward to append. And now when we change our range to toString, we can just call for each while instead of copy using the string appender, and that way we naturally get the contiguous chunks of our ranges into the string. That was the wrong direction. So if we have, what we have is a range of spans, and we join it using the string appender sync, after inlining, this turns into the two nested for each whiles of the join. And then, where do I keep going in the wrong direction? And then this, the inner one is a span. The string appender knows how to handle the span, so we just call chunk. And this gives the entire sync the opportunity to get the chunk and process it using append instead of going character by character. So syncs really are the better output iterators, right? Output iterators are kind of clunky, where you have to implement like operator ++ and operator star, and they don't have any ability to receive chunks, only one element at a time. Whereas if you put a sync, you only need to overload the call operator, and then you can potentially handle the arbitrary chunks, right? And so the standard library in the future should sort of support the output iterator interface only like as a fallback, but crucially it should allow syncs, right? So instead of having the back inserter, you would have an append to sync, which provides the appropriate chunking for this particular container. So like for vector and string, the chunks would be contiguous, and then you can mem copy them in. But for example, if you have a range of like lists and you want to like append that into a list, you might be able to call splice in there when you receive a list, which is a chunk. And this just makes it a lot more efficient than going element by element. This also means that like when we express pipelines, they should also express this chunk. So if we call read file, we're having big contiguous chunks. We transform them and keep them. This makes it not contiguous, but when we join it back together, we've got tiny contiguous chunk. But they're like really tiny, it's like one string at a time, right? And the strings are usually one character. So we don't really have a good way to handle entire chunks, append them as one chunk. Instead, we just got the tiny things. So what would be a better way would be something like this. So we try to like keep the chunks by, instead of using the transform, we are splitting it at the tab character. And now we've got a range of potentially contiguous chunks in there, and then we're joining them back together with the appropriate separator and passing them. And this keeps the chunking property, because join with, again, is just like two nested loops. Instead, we also like put in the separator. So this keeps the entire inner range as like one contiguous chunk that can potentially be handled. The only problem is that this code doesn't work because split requires a forward range and read file as input. And if we were to use lazy split, it does not keep the contiguous chunks. And even if this was somehow made possible, the read, like once we split it, we've got a subrange of iterators into the read file and lost all the contiguous chunks that the read file had to begin with, and we will never get them back because we downgraded them to iterators, and you don't have a for each while for like a subrange. However, in this particular case, we are fine with treating each contiguous chunk separately. So instead of having read file that gives you the characters, let's imagine we also have read file buffers, which gives you a range of spans. And these are the contiguous chunks of our file. And then the read file is just read file buffers and join them back together to get all the characters. And then we can implement read file normalized like this. So we get only the buffers, which gives us a range of big chunks. And then we transform each chunk in isolation, splitting it, which keeps it contiguous chunks. And so when we join it together, we keep the contiguous chunk property. Now we just need to join the entire thing back together and convert that to a string. And after all the inlining, we will get each contiguous chunk, which is the span of all the non-tab characters, as one thing, pass that to the chunk member function of our string appender, and be able to append it all at once. And in fact, we can even write like a pure generator of read file buffers in terms of read file. All we need to do is to wrap our range, provide a custom for each file that provides a custom sink, which only handles the contiguous chunks and passes them as single elements to the sink. So with generators, we're even able to like undo a join. Right? So even if we only have read file, but it's implemented in terms of contiguous chunks, we can extract the contiguous chunks and undo the join. So that's really nice. Questions about the so far? Okay. So the for each while customization point is really nice. It provided us the ability to like split the range into chunks, express those chunks, optimize loops, optimize output iterators. It's like a really powerful facility. But it's even more powerful if you look at problem 2. So here, some colleague had a problem where they wanted to describe an SQL schema in some sort of compile time DSL and then generate the appropriate SQL statements at compile time. So for example, he had a DSL that looks something like this. So this defines a table called people that has 2 columns, ID, which is an integer primary key, and name, which is some text. And then you can call create, and this will give you the SQL statement that you would need in order to create this table in an empty database. Now there are 2 primary problems we need to solve before we can actually tackle the main problem. And they have to do with the underscore TC. So the first problem is the difference in compile time versus compile time. Right? So a compile time expression isn't always a compile time expression. If you're in a constable function, the arguments aren't constable. So the first line compiles because you're just in a read context, you're just calling it, everything works. But in the second one, you have a constable function that takes the string, and this is an error. Because even though the string is ultimately a compile time constant, it's not one within the body of the constable functions. And this is just a fundamental limitation of the way C++ works. And the way to fix that is to sort of embed the relevant information in the type of the argument, not in the value. Because we don't have the value at compile time within the body, we only have the type. And so we need to put the relevant information in the type. And so we'd say that we're doing, in the body of constable function, we're sort of doing early compile time, and then we don't have the true compile time values, only outside when we do late compile time. And so if you want to bridge the gap, you have to put that in the type and not in the value. And so the second problem has to do with string literals themselves. They're really bad ranges. What's the result of size ABC?
4.
4. Because it's an array of 4 characters, including the null terminator. And this makes it really awkward if you want to use string literals in ranges. They always have the null terminator there. And the solution for that is, well, you need a custom type for string literals. Putting both problems together, we want a custom type for string literals and a custom type that sort of expresses the value in the type so we can have them in the early compile time context. And the answer is literal range. So literal range is simply a thing that is like NTs. And then we have begin and end, which simply synthesizes an array. Yes?
Just quickly, why didn't you wrap it with string view and then take this?
Why didn't I wrap it with string view? I didn't wrap it with string view because string view doesn't put it in the type.
Oh.
Right.
Oh,
I also
for
need
the size T, I mean. But for the size T, it's fine. But
for the size, it would only solve the size. It wouldn't solve the second problem. So I could wrap it in like an array. And then we've got the size at compile time, but we wrap it in a literal range, and then we have both the size and the values in the counter in the type, have them accessed in the thing. And the implementation so we know got the UDL, which simply creates a literal range out of a string without including the null terminator. And the TC in there, that's just our namespace name, because we put this operator at global scope, so you don't have to use the using declaration in order to use UDLs, which is just always really awkward. So we just call the TC, put it in the global namespace, and then it just works. And so now the size problem solved, and the size of the literal range parameter is a compile time expression, which means it is something we can work with. So this brings me to compile time sized ranges. Because at the core of the SQL thing is this object, DSL, and it specifies just some SQL object like a table, which has like a type, which would be something like table, and a name, and then it is create function, and we really want to write code like this. Just like create, the type, the space, the name. Right? But this doesn't work. Like you can't just concatenate compile time stuff and get a string literal out of it. Right? And there are like various ways to solve this, but the way that we really want to do is we just want to use range algorithms. Like we are heavily built upon range algorithms, and we just want range algorithms to work in this case. Because the way we concat stuff is we call concat. And now we just want to turn the concat, turn that into an array, and turn that into a result. We have to turn that into std array because we can't turn that into like a vector or a string, because this would be a dynamic allocation. And even though we are inside a constable function, this still sort of leaves the compile time context. So we just can't have a string in there, so we need a std array. So we really want this code to work. And so we first have to iterate to turn a range into a std array, which has the obvious problem that like this would be the overload, takes a container of type and size t, and it returns a container of the value type and the size of the range. Unfortunately, range is a parameter which is not const expr inside the function, so this just doesn't work. Or does it? Ever since C++23, which adopted PP 2280, it just works. Right? You can write code like this. So you can write a concat of like some ranges that have a size which is sort of known at compile time, create them in a local variable, and use the size in a compile time context. Because this paper relaxes a rule where like you can use a reference to a runtime value at compile time as long as you don't access any sub-objects or the value which depends on runtime values. But in our case, the size function of literal range does not access anything of star this, so it can be called on a runtime value at compile time. Array has a size which is static to begin with, so it doesn't access anything at all. And concat view gets all the references to the each individual ranges and sums them all up, but this doesn't actually access any values of the ranges. If size doesn't require any properties, then this just compiles. Right? And this is like really magically, but also really convenient, because it means that the code just works. The only thing that's missing is like some sort of concept for that. So like a compile time size, the context per size range, which is just the range where we require that we can call size and get a compile time value regardless of the compile timeness of the reference. And then we can also write code like this. So we can say, given the type of the range, which is context per size, give me the size. Except this doesn't work because declval isn't context per. And there is nothing stopping us from making declval context per now. It could simply return a reference that cannot be read at compile time just to make this code work. But it isn't, so we need some workaround. And the workaround is really magical. Is we create a lambda, which takes the range, and now we've got a reference inside the thing. And then we call range size. And because range size is a compile time expression that doesn't depend on the actual value, we can put that in the return type. So we have some way a return type that is sort of dependent on the parameter, but it's only dependent on the type of the parameter because we don't actually access anything. Then we can call the lambda of declval in a decl type context because all the information is in the type, and then we get the value, and then we've got the size. And this is the context by declval pattern, which just takes a function, synthesizes some references, calls the function with the references, and it works as long as the function doesn't actually need the references. And so with that, we can simplify that by saying context per size is just get me a range to reference and call size on it. It would be a lot simpler if declval were const expr, but it isn't yet, but this works.
Do you know of anyone that works on this?
No, I tried Barry to work on that, and I tried Hannah to work on it. I wasn't so successful yet. I'm going to try to push them again.
Cool. You could work on it?
I could also work on it. Yeah, technically I could also work on it.
Just saying.
Yeah, but you know, I'm sharing a subgroup now, which means I delegate.
Oh,
Yeah, you could work on this.
Congrats.
Yeah.
Thank you for volunteering.
Yeah.
Would context for declval require that to be considered an unevaluated context in a static assert, or how would that work?
I mean, in this implementation, we are only having unevaluated concepts. So the declval.
No, I know that the decl type
Yeah.
works, but what you're asking for.
Yeah, so the way it would mean that declval would be allowed to call at compile time, it just gives you a reference that you can't access.
Okay.
Right? So like one way that would work is you can say declval returns a reference to a declaration of a global variable that is not const expr. Right? And then that one is never defined, and then you can just have a reference to the thing, and that would just work. You just can't have undefined variables of arbitrary. Like I can write a const expr declval int. I can write a const expr declval float. I can't write a const expr declval template t.
I think you can actually implement that now without compiler intrinsics.
Yeah, it would require some sort of compiler magic.
No, I don't think you can declare an extern const t.
I can't do it inside the function. I tried that. because then the name mainly doesn't include the template parameter. So if you instantiate it twice, you've got the same variable
But
twice.
you can have an extern const t value template.
Can you?
Yes.
Okay, then it might be. So you volunteer to write the paper then with that implementation?
Okay. Really quick, just I blanked on it. What's standard CW in this case?
It's essentially an integral constant.
Okay, thank you.
Yeah, it's upcoming. Might make C++26, might not.
26. It's Zach's paper.
Yeah, but it's like stuck. LWG has a lot to do, so it might not make wording review.
No. I think
Yeah, but talk to Jeff. He said he won't. It won't.
I know.
So this works really nice, but unfortunately MSVC hasn't implemented that. So if we want const explicit before that, we have to actually go a knowing route where we like have a variable template, then we specialize it for ranges like array. We can just specialize that, and otherwise we've got this semi-generic thing where we can say, hey, if size gives you like an integral constant, then we can just extract that out of there and just manually do that. I've written a blog post about that, how that works. There's some cute trick which doesn't require you to duplicate size, like once returning an integral constant and once returning a one-time value. So read that about more details. So it is, we have implemented that pre-C++23, but like it's just a not nicer with the other thing. No matter how we do it, we can now write to array. So we can create a container, we can get the size because it just works for compile time sized thing. We can just access it, and then we just copy stuff over. This, of course, requires that everything is default constructible. So a proper implementation would look like this. We create an index sequence, we create an iterator, and then we just index into the iterator. And this uses like the square bracket operator for simplicity. This isn't really necessary. You can just call star. It's then do the post increment. You can make that work for forward only. Just for simplicity, you sort of have to you can unroll it into a pack of values, pass that to the aggregate initializer, and have an array of a compile time sized range. And this means that this code like this just works. We concat the stuff, have a range, convert that eagerly into an array, and then we return that as a string. However, it wasn't so simple. Because this isn't the full code. So first of all, uses a convenient function where you don't have to vary with the space. So concat with is just like join with, except it works on like a pack of ranges instead of a range. The implementation is pretty straightforward. So it just repeatedly concats with like the separator in front, unrolls that all. And our implementation of concat detects when you have like nested concat views and flattens them out into a single one. So this doesn't create a concat of a bunch of concat views. It's just a single concat view of range 0, the separator, range 1, the separator, range 2, and so on. And so we've got the thing and don't have to worry about spaces. So that part isn't a problem. What is a problem is the additional qualifiers that an object may have. And those ones may be empty. And so my colleague didn't want the unnecessary spaces. So instead of calling concat with, he called concat non-empty with, which filters them out. And concat non-empty with, that cost me so much headache, because that's the implementation. So it takes a separator and a pack of ranges, and first of all, it turns them back into a range. So it calls make range, we'll see the implementation, that just takes a pack of ranges and returns a range over all of those. This is because we want to use range algorithms all the time. And so we then, once we've got a range, we can call filter out the empty ones, and then join them, this time using join with the separator. And so the problem with that is that this is not at all compile time sized. And if it's not compile time sized, we can't call it to array, we can't do the thing. So one way to make it compile time sized is the particular case of ranges that are compile time sized. Because then we could write something like this, where we just need to filter out from the pack the empty ranges, and then forward to concat with, which then just works. And this is what I like prototyped and gave him just so he can continue working. But like, I really wanted to make this work somehow, right? Just because we want to do everything with ranges. So just, if this could just work, that would be nice. And so the first hurdle is the implementation of make range. So this was the implementation of make range when I got started. So it just takes a bunch of ranges, computes the comment type, and pushes them all into an array. And this works. Except it just erases the type information and turns it into a comment type. And so when we call make range of like our fancy UDLs, the result is an array of span of constr. And so we no longer have the size expression because this was only encoded in the type. It's no longer a constant expression. It's type erased into one template. And so we can't use an array, because an array would force them all into a single type. Like, we need the tuple of all of those ranges. But a tuple isn't a range. And hang on, I'm getting a text message.
No problem.
Yeah.
Wait.
I have to take this call, sorry. So, tuple isn't a range, because like, what would even be the iterator? Like, even if it had the iterator, like, what would it dereference to, right?
Stood variant of those types.
Yeah, a stood variant of those types, right? You could do that. You can write a tuple iterator that dereferences to stood variant, but like this is overhead, and like we don't really want overhead here right now. So what wouldn't have overhead is just providing for each while. Because for each while you can get the indices, you can invoke the sync with each element. And then you just pass it the sync whatever is the current element of the tuple, and so the sync is now templated. It's a templated lambda. And this is in fact what we did. And we call those heterogeneous generators. So we've got the homogeneous ranges, ones with begin and end, and optionally for each while as an optimization. A heterogeneous generator is something that only provides for each while and no begin and end. A range has like a single range value t, and a generator has a variadic type list of the generator output t, like all the potential types you can get. With homogeneous ranges, you can use all the ranges and views. With heterogeneous generators, you can only use the ones that only require for each while. And we did that for as many as possible. So like you can use filter, you can use transform, you can use for each, you can use copy. They all work because they don't require iterators, they just call for each while. With a range, you can use range-based for loop. With a heterogeneous generator, you can only use for each while with a generic lambda, because the type changes, right? And so every homogeneous range is a heterogeneous generator, but not vice versa. And we've implemented the appropriate traits in that sense. So we made tuple a heterogeneous generator, which means we can just call range algorithms on tuple. That's really nice. We've also made index sequence one. And then we've got a range over a sequence, and this gives us a range of like early constant values. So like it's encoded in the type using the constant wrapper, and then we've got a range of compile time integers that we can do stuff with. We've also made like empty list. We made that a generator, which gives us a bunch of type identities. And so we can do metaprogramming on types just using range algorithms. So we can filter type lists, we can transform type lists with the same code we would like filter or transform runtime values. It's really useful. Case in point, Matt Gottbold gave the keynote at ACCU 2025. And like he wrote an emulator for the Z80. And he said he really wants to write code like this. So he wants to like turn each opcode, compile that into a function that would emulate that opcode. Right? And so he had code like this on the slide where he said, okay, so we iterate over each byte, iota 0 to 256. We transform that, that byte into the appropriate instruction, so we decode the instruction, then compile that instruction into a function pointer that will execute that instruction, and then get that all into an array. And like he had this code on the side, but he said, unfortunately, this isn't C++, this doesn't work. We don't have the opcode at like early compile time in there, so we can't use that. We can't turn the entire thing into an array, and so it doesn't work. But we can just make that work, because make integer sequence, it's a heterogeneous generator, so we can use that. Then we've got the opcode at the compile time thing. We can decode that into the instruction. We can compile the instruction into a function pointer, and we can turn the entire thing back into an array. And this is exactly the code he wanted to write. Right? It just requires heterogeneous generators to work, but then it just does. Right? This is valid C++, assuming that you've implemented the this is valid C++ in terms of our library. So that's really nice. Yes.
So for users so you basically propose this concept for the standard, then users could, and then we can like have some of our algorithms support this. For heterogeneous generators.
I'm not proposing it. I'm saying we did that, and it's in some sense a missing range concept. I will talk more about whether I want to propose that later.
Oh, okay. So you do have something in this scope that you want to. That's really cool.
And so once we've got that, we can then like special case various things. So for example, this is the filter view for each while implementation, and this one only works also for like heterogeneous generators, and then it gets a templated lambda, and so that's potentially a different type. And then we can say, hey, if the predicate is like a compile time thing, filter at the compile time. And this avoids the instantiation of the sync with a type which does not match the predicate at compile time. And then we can sort of do a filter based on the type without instantiating the stuff. which means we can sort of turn a tuple, filter some types out, and create it into a vector. Right? And like that's really nice. Like we do that multiple times. For our specific problem, it means that we call makeRange, we turn that into a tuple, and in some sense, this is now a compile time sized range where all the elements are compile time sized. So first hurdle done. Next hurdle. After we filter it, it's no longer compile time sized because filter isn't even a sized range to begin with. So can we make filter size? Or we could provide a member function size just called countif. This compiles, it works. The problem is it violates the semantic requirements that size is O1, right? This is a loop. This is most certainly not O1. We can do this. We can say the base is contiguous sized, and now the loop is O1 because it's a compile time constant. Like it's potentially a big one, but it's technically O1. But like still that you might feel a bit sketchy. So you could say, okay, we do this only if the predicate is like a compile time evaluated thing. So we do that if you have a contiguous sized range and all the potential output types of our base range are ones where the predicate evaluated on like some object of that is a compile time constant. Because then the countif is just an O1, but it's like all compile time decisions, right? So this is just like a bunch of like sums. So this is a hopefully optimized O1. And this would work if you have cplusplus23. In cplusplus23, this countif then even is potentially a compile time expression if everything just falls out nicely and it doesn't actually dereference it. But we don't have that. We need to like specialize the variable template somehow to get the context precise. And the problem is, again, here we're calling Deckelval in an unevaluated context, which just doesn't work. So we can't do that this way. And this is actually a good hint that we can't do that because these conditions aren't enough to have filter be context precise. It's not enough for the base range to be context precise, and all the predicate decisions are compile time decisions. That's still not enough. And it's not enough because of a range adapter, we have conditional range. So for example, like take a step back, consider this problem. This is a famous like interview question, like giving a word, reverse all the words, but keep the overall thing the same. This can be done by like taking the string, chunking it into like words and non-words, reversing the words and like keeping the rest unchanged, and then joining it back together. And the problem with this implementation is that this doesn't compile because in the lambda of the transform, at one point we're returning a reverse view of the chunk, and in the other branch we're returning a chunk. These are different types, so it doesn't compile. Right? We have to make it the same type by, for example, eagerly turning them into strings. This isn't nice. It involves memory allocation and just eager work. So we've got a range view called conditional range, which is just a single type, and like if you iterate over it, depending on the runtime condition, you will either iterate over one or the other, right? So it just selects between multiple ranges based on a runtime value, and it's like suitably optimized that like if they have the same iterators, it will just give you the same like appropriate begin end. But if they're different iterators, you've got like an iterator that's like a variant of the appropriate iterators and that sort of thing, and this makes it work. And this is just a really nice view that allows you to like conditionally select between multiple views. And like I plan on bringing that to the standard because it's nice in cases like this. The problem here with filter is that this creates a problem. So we've got a generator of size 3 and another generator of size 3. And then we can call a conditional range that like conditionally selects between gen 1 and gen 2 based on some runtime value. And the size of this one is still 3 at compile time because each of the branches have a compile time size 3. However, when we filter it and want to say, hey, give me only the integers, the size no longer is a compile time expression because depending on the runtime value, the size of the filtered range is either 0 or 3, right? Depending on whether you have gen 1 or gen 2. So even though we have a compile time sized range and the predicate only depends on the type, filter isn't compile time sized because this is not enough. Like there's another condition. And so filter can only have a compile time size if the range has a compile time size, the predicate only depends on the type, and we can know the type of each element at compile time without relying on like some runtime branch. And so we need some way to implement that, and for that we need to say, hey, filter underlying range, what's the end type? And for that we've got the concept of a tuple generator. So a type, which is a generator, which is it implements for each while, which is compile time sized, and it is tuple-like, is what we call a tuple generator. And then we've adapted the appropriate views to like be tuple-like generators when possible. So a tuple-like generator is sort of the random access equivalent to an input range, right? So we've got generator, which are sort of input ranges, and tuple-like generators, which are random access ranges, because we can get like random access just only at compile time. And so this is like a really nice comparison. So like for a generator, you can call for each while. With a tuple generator, you can call template for. Upcoming CppNow, it just does like unrolling of each element. And for a range, you can use the regular range-based for loop. And so this is like sort of the difference in like power of the three concepts. And for us, tuple generator means we can actually implement the compile time size of the filter view. So if the base is a tuple generator and the predicates are only compile time size, then we can do the countif completely inside a context by decibel, just depending on the size, just give me the appropriate element of the base range. And if all of this works, then filter has a compile time size. So this excludes the conditional range with a runtime condition, because then we can't implement a get on there because it would know, like, would branch at compile time, would branch at runtime. But if this is not the case, then we have a compile time size. And in our case, all the conditions are true, so our filter now has a compile time size. If we have a compile time size, we can also provide a get, so we can make filter a tuple-like and say, hey, it's just a matter of like forwarding the index to the appropriate base index, skipping over skipped elements. And this can be done by just computing a single lookup table at compile time and then indexing into that to skip over the elements. And with that, we can call main range, we can filter it, and we're still having a compile time sized range with compile time sized elements. It's just the join view that creates the problem. Yeah.
Can you go back to 85? I think it was just wanted to see that syntax template.
Yes. Interesting. Yeah. So this is upcoming, and it essentially expands to like get 0, get 1, get 2, get 3, like one after the other. Just literally copy paste the body the appropriate amount of times.
And it's like thanks.
Okay. Yeah. So. Yeah.
Just a quick question. So the tuple generator, in your case, specifically here, you have the same types for the tuple, right? It's all in, not heterogeneous.
It is heterogeneous because because essentially what we're having is we've got a bunch of literal ranges which have each a different type. We turn those into tuple, and then we have a lazy tuple of only the subsets that are non-empty.
I see. It's a type of the ranges, not the type of the elements.
Yeah. And like the lazy part is a bit in quote because we're doing the actual access at compile time. Right. So it's like
lazy compile time.
So like at runtime, this is eager now, but it's just forwards to the laziness. So join. I'm just gonna focus on so we're using join with, but we actually implement join with in terms of join by just having an interleave one that takes the range, interleaves another range, and then we're flattening that out with join. And the problem really is join. So let's focus on join. Unlike the standard, we were already able to provide join sized, provided that the outer range is sized and the inner range all have the same compile time size. Because then we can just say the size of the join view is just the size of the outer range times that same size of the element. This is an O1 thing, it just works. But in our case, the elements that we're joining over are potentially different size. So I need to extend that definition. But it's not too hard because what we're having is like a tuple, so we can do a fold expression. So if we're having a tuple generator of the base range, then we can also make it O1 size by just adding the sizes of all of the elements. And that's still an O1 size then. And when I wrote this, I had a bit of a deja vu. Because I wrote this same exact code just a couple of weeks ago. Like specifically the case of like computing the size of a tuple generator of a join. This is the same exact code I had for concat view. If you're joining a tuple generator and you want to get the size, this is the same as when you join a concat view. In both cases, you have a tuple of ranges, you sum all the sizes. And it goes even further, because like this is the for each while of the join, the two nested for each. And since tuples provide for each, this is our implementation of for each while for concat. We have a for each while of the tuple, and then a for each while of each element of the tuple. And this is really because concat is just a join of a tuple. two separate things in the standard library, because there's a difference between like a tuple and a range, but with the generators, we've been able to unify that. And so a concat is just a join of a tuple. And so I've actually changed the implementation. Start over?
From the beginning.
Yeah. And so we've actually changed the implementation of concat now to just be join of a tuple. And so join is sort of like specialized for like 3 cases now. So the tuple-based join view, this is the same as concat view. The iterators behave like slightly differently, so it's like a separate implementation. The range-based one, that's just the plain old join view. And then the generator case, so because we support join on like stuff that doesn't have iterators, that's just a shared thing that implements for each while and size, and it's the same whether you have a tuple-like or range-based, because it is ultimately the same thing. And this further means that like the hacky code that just filtered out on the range and the fancy one that uses the range adapters, they are the same algorithm. And I don't mean they're isomorphic. I mean they're literally the same algorithm. Because in the second case, we're calling join on a tuple-like range. And that means we're having a concat. Because a concat is just a join of a tuple. And so the compiler actually spits out the same code, because if you're having a tuple-like range and we're joining it, we're essentially doing a pack unrolling and concatenating it all together. So this is one and the same algorithm. The implementations are entirely equivalent. It's just we're able to use the fancy range adapters instead of having to like filter out a parameter pack. And like, that made my day. And it means that like, after all the necessary infrastructure updates in the library, all that I actually needed to do to make concat non-empty with work was just to add the missing context bar. And then it just magically falls out of the new implementation. And like, that's really cool. Questions about that? Okay, so the bonus. I gave a talk about functional programming at ACCU, and one of the examples I had was this. Some code, this computes the first Fibonacci number that's bigger than some threshold. And the way it does that is it gets all the Fibonacci numbers by having an iota of indices and transforming each one into the Fibonacci number. And like, this is not very efficient. I optimized that later on in the talk, but like, let's look at this example. So what we're having here is an example of an infinite range. All Fibonacci numbers is an infinite range. But then we're like only accessing, we only loop over it like a finite amount to get the first one that's bigger. So it all works out. We don't have an infinite loop here. But we're having an infinite range. And so there's something funny about infinite ranges. If you look at the standard. So the standard defines ranges as being an iterator and a sentinel that designates the beginning and end. And then we denote that using like the interval notation, where we've got an iterator I and a sentinel S. And essentially we can like keep incrementing I until you reach S. And so if this happens, we can say that a sentinel is reachable. So a sentinel S is reachable if we do like plus plus and I a finite amount of times, and then I is equal to S. If we do it a finite amount of times. So if you have an iota, we can do it an infinite number of times. And we'll never reach the sentinel. This makes the sentinel not reachable. And in fact, the type of the sentinel is unreachable sentinelity, right? Because it's not a reachable sentinel. So far, so good. However, the sentence then continues, requirements general /10, and says that if S is reachable from IS denotes a valid range. And the result of the application of library functions to invalid ranges is undefined. Oh. This means that this code is undefined behavior, because we have an invalid range and we're calling a library function on it. It means this code is undefined behavior, because we have an infinite range and we're calling a library function take and the pipeline operator on it. It means this code is undefined behavior because we're calling .begin, which is a library function on an invalid range. It means this code is undefined behavior because we're calling the destructor of iota view, which is a library function on an invalid range. And so this came up in Hagenberg and SG9, and like we took a poll. Essentially, the standard library should not provide facilities that only cause undefined behavior. And like it passed. It was like the actual poll had like slightly more nuanced wording, but like in a nutshell. We provide a iota view, but you can't actually do anything with it without causing undefined behavior. And like that's a bit unfortunate. But like how to fix that?
Sentinel is reachable. Just have to wait a long time.
No.
I get to that.
Okay.
So
Is this
let,
the same kind of undefined behavior that filter view has, where it's like it just doesn't do what you want?
Yeah. Yeah, it's undefined. So the problem space is this. Yeah, so the problem space is we've got like truly invalid ranges. Like if you do a subrange of array plus 10 and array, that is an invalid range. And that using that one should be undefined behavior, right? Similarly, if you do vec1 begin and vec2 end for two different vectors, that is undefined behavior. And we want to give implementations the ability to diagnose them, so these ones should be undefined. So these are truly invalid. Then we've got two infinite ranges, repeat 42 and iota of an unsigned 0, right? You can just loop over them forever. No undefined behavior there. Then we've got sort of ranges where dot end lies. So it's like iota of int. Even though end is unreachable, eventually you will have integer overflow, which is undefined behavior. So it's not infinite, it's just end lies about the true size. And you can also like use a subrange of pointer with unreachable sentinel. If you like don't like bounce checks and like to live dangerously and just like trust me, I know what I'm doing, I will not go too far out, right? And then we've got ranges where we don't know. Like iStream could go on forever, depending on which file you're reading. Generator T could go on forever, depending on what the body of the generator is. And as we'll see, it's going to be really hard to like find wording that properly distinguishes those cases. And then, of course, the problem, like, what even is infinity? Like, this is an infinite range. Right? You will just repeat 42 forever. This will print 42 forever. But like, is this an infinite range? I mean, like, surely at some point the user is gonna stop providing us input. But like, it might not, and then this is an infinite range. Do we care about like when talking about ranges whether this is an infinite or finite range? Because it like really depends. And like eventually the universe will end, so the loop will end. You know, like, is this an infinite range? So we got a range where like we say we at the end when we roll 6. We could never roll 6. It has probability 0, but you know, just because it has probability 0 doesn't mean it doesn't happen. So we could never roll 6. So is this an infinite range? And then we have to distinguish between like, okay, so like, if you're having a server, we're like looping over the input, processing it, and printing it out, right? This is what I call infinite usage. Like, this will run as long as the server runs. So this is sort of an infinite loop. But then it's like really convenient to just combine an infinite range with a finite one. So like when you zip them, either by a zip or a transform, it's really convenient to be because it just goes to the shorter one, so you don't have to worry about providing the upper bound, and this will just give you the range and its indices, right? And in our case, we call find, like in the example before, we called find if on all Fibonacci numbers. Eventually, a Fibonacci number will be bigger, and then we stop. So this is only a finite usage of an infinite range. And like we might need to distinguish from that. So let's try and attempt some definition. So let's say we introduce the term infinity sentinel. This is a sentinel where like no matter how many times you do plus plus I, you will not encounter undefined behavior, and I equals S is false. And this is repeat, this is iota of unsigned, this is potentially an iStream, this is potentially a generator, right? They might have like an infinity sentinel, but they will never reach. This does not cover iota of int. Eventually you will have undefined behavior. Similar for the subrange and for the two invalid ranges where we just provide nonsense to the subrange constructor. So those ones are different. For those ones we've got like an unbounded sentinel, where I equals S is still false, but you can only do increments a finite amount of times before you have undefined behavior. So the true range is only like a finite prefix of IS, we just don't know the bounds, right? Which is unbounded. And this is the iota of an int of 0, because you will have integer overflow if you do it int max times. This is the subrange of the pointer with the unreachable sentinel, and potentially a std generator. But, yeah?
Just a quick, like, is it true to say that, like, this is not infinite range, but it is finite range is only known when does it end in runtime?
Yeah. This is not an infinite range.
Yeah.
This is a finite range. We just haven't provided the correct bounds. Yeah. The problem with this definition is that it would also allow this nonsense. Like if you do array plus 10 and array, well, there is a finite prefix if you do it 0 times under this wording, right? There is if you do a vector of like two different iterators, there's a finite prefix. Whenever vec1 ends. And like any iterator sentinel pair where you can like compare them is now an unbounded sentinel, which makes it some sort of valid range. It's just the finite prefix is just 0 because we only have an iterator. And so like this definition is too weak. Like we allow too much. So we could say, okay, unbounded sentinel, you have to have the type unreachable sentinel. And then you can only do it a finite amount of times. And this still allows the two cases we want. And it prevents the invalid ranges. Because here we're not using unreachable sentinel, which means that like we just have nonsense in here. Because we didn't say that we want it. Like if you wanted to say, I want all elements from the vector, but trust me, then you would use unreachable sentinel and not the end of some unrelated vector. Right? The problem with that definition is this would prevent the generator of T as being an unbounded sentinel. But the question is, do we care? Like, generators can be infinite, and generators can be unbounded by having undefined behavior at some point. And like, at the level of ranges, do we care about the unboundedness there? Do we care about this undefined behavior? Is this a problem in a range definition, or do we just say, well, it's just the body of the generator that encounters undefined behavior? Like, do we care? And like, this is like, I could see it either way. I saw nodding in other cases. Yeah.
Yeah, it's like this. We've got a level problem.
Yeah.
We're trying to solve the halting problem
Exactly.
in library wording at the range level.
Yeah.
Where it's like, it's the problem exists in the body,
Yeah.
not in
Yeah.
the.
Yeah.
Have you considered, instead of requiring the sentinel type to be exactly unreachable sentinel T, using the trick with the concept to check that the comparison with the sentinel is not data dependent?
Yeah, that could be that could also work. It just also wouldn't work for generator.
Right.
Because generator type raises it. But like, yeah, that would be a more like, I would consider that isomorphic to the definition. And so like at this point, I was really glad that I titled this talk "Missing Range Concepts," but like, because like I don't have a solution for that yet. This is gonna something we have to work on in the standard, because that isn't even the entire problem space. Like, what about difference type? If you do ++ I an infinite number of times, you will exceed pointed of T when you do this abstraction. But like, do we care? Like for finite usage, it doesn't matter because you're only looking at a finite prefix. And if you're having a true infinite loop, then maybe. But also, it's like not a new problem, because on the 32-bit system, you can have 3 gigabytes of memory, and then you can have a span of 3 gigabytes, but you can't do the pointed of T because it doesn't fit. And so like, this is already there. We just sort of pretended it doesn't exist. And we might then just pretend that more officially that this isn't a problem and not all differences fit in the difference type. But then like, what about this? So we've got an iota view that starts at 0 and an iterator that is 4. What is the difference? 4, unit max plus 4, 10 times unit max plus 4. Like we could, like it cycles. We could like keep going over and like have like an arbitrary modulo. So we probably want to say that the difference type is like the lowest difference because like the unit max, like what does it bias, right? It's fundamentally cyclic. So once we figured that out, and like once we like re-specified the appropriate algorithms to handle infinite ranges, because right now there are some wording problems, so we'd have to like go over that with a fine-tooth comb. Then like what we really want is some sort of new sizing hierarchy, where we've got the sized range concepts for ranges that have a known finite size, the infinite range concept where ranges has an infinite size, and we know it has an infinite size, and then just the general range concept where the range could be finite, it could be infinite, it could be unbounded, we just don't know statically. Because such a concept would be really useful. For example, the parallel algorithms require sized ranges in all inputs, which means code like this doesn't compile. It's really convenient to just say, okay, I want to like transform with the range and some index, but you'd like iota isn't sized because it's infinite, right? But once we can detect that statically, we could relax the requirement because just use the size from the range, right? The size is there, just that one is definitely the smaller one. Similarly, we could have an infinite range, and when we take a finite prefix, we don't have to worry about bounce checks, right? Because it's a finite thing, could be optimized. And so like, this is what I actually proposed. And then during the discussion of this paper, it was pointed out that like, it's all nice, but like infinite ranges are undefined behavior to begin with, so why even bother? So that was fun.
Yeah, except they're only undefined behavior because we said so.
Yes.
Because they're actually
Yes. Yes.
That
Yeah.
should be pursued.
Yeah. We're gonna take care of this hopefully this
Well,
decade.
We've spent years now because we said undefined behavior in filter view, where there's no actual undefined behavior. It just doesn't do what you want.
Yeah. But
So yeah, but for parallel algorithms, you have a workaround even today, right? Because you can only say iota 0, range
Yes.
RNG size.
yeah.
Because we require for a parallel range algorithm require both ranges to be sized.
Yeah, exactly. It works. It's just more annoying. Like if you had infinite ranges, you could allow this.
The user, I mean, iota. I'm not sure if that's the correct example. Repeat is going to be the more
Okay.
interesting one. Yes.
Okay.
But
Okay.
still, fortunately, repeat also has bound, so you have a workaround.
Yeah. You have a workaround. Like it's not a critical thing. It's just annoying, and the whole this is undefined behavior to begin with is kind of awkward.
Yeah, there are types you can give to iota that are perfectly incrementable as well, but I think weekly incrementable is overspecified because, like, if you try and put a day of the week or a month of the year, which you can increment and decrement, they don't work in infinite iota ranges.
Right. I mean, nothing works in infinite iota ranges. So,
No, but assuming it were defined, it still wouldn't work because of the other constraints.
Yeah. So to conclude, what should actually be included in stored ranges? Conditional range, nice little view, should be in there. The for each while customization point for optimizations, this should definitely be in there. Like this is just a nice performance speed up that you can get essentially for free. The user doesn't need to care. It's a bit unfortunate that we don't get that to the range-based for loop, but then maybe once it's been in the library for a while, we can go back to evolution and say like, hey, now we've got this thing, we've got a bit stronger motivation. Building on that, sync-based appenders as better output iterators. The ability to receive chunks is really critical, it's really nice, it works well, and we can just build that on top of the for each. Compile time-sized ranges unnecessary, and then we can also provide 2 for the stored array just as a nice convenience thing. And of course, a fix for infinite ranges because this is just embarrassing. And that would probably just be a defect report back to CppNow. Now, I don't think the generators or the heterogeneous generators even, they are probably not a good fit because they're like a wild departure from existing range concepts because we've got like ranges which don't provide iterators. We've got ranges that don't allow the for loop. We've got potentially ranges that have multiple value types. And like this is like such a wild departure from like everything in ranges and everything in the algorithm. And it would require like so many changes to wordings to carve that out, to allow that. It's not a breaking change, it's just a lot of work. And I don't think it's a good fit for the foreseeable future with the way the standard library works. And there is a workaround. Because the workaround is you can sort of make it homogeneous by like using a range of stored meta info. Because reflection isn't typed. You can, instead of having a range of like types, you can have a range of meta info of reflection of types. And that you can work with the range algorithms. And then you can like stay it on meta info, end up with an array of meta info, and then turn that into the types as like a single thing outside the range world. So this sort of like untyped nature of the reflection stuff provides like a sort of a workaround to like keep the range algorithms and do it like this. So it's like not a critical thing.
And if you can associate a value with that type, you can do the calculations that you want.
Yeah, exactly. Like you can have a reflection of like a compile time context and do that. So like you can type erase everything, live in an untyped world, use the range algorithms, and then in the end turn that back into the appropriate things that you want. And so proposals welcome. SG9, the range study group, we're really nice. We're a really small group. We're gonna point out so many edge cases in your paper that you haven't thought about, but we're going to do it in a very nice way. So like, if you want to get started with standardization and want to work on this space, I welcome any proposals in that. And if you want to work on like sort of the bleeding edge of ranges, we're hiring too. I think so. Thank you.
So first of all, that's awesome talk. I loved it. And as always, I love great things. So I just wanted 2 things. First is that we recently made infinite loop non-UB. So I think to be aligned with that, I would hope to see us also making the calling of functions on. So I think that would make sense to align that. And second, I I see your workaround. Like I agree with you about the workaround. I still see value in having the generator concept exposed to it. Like what I'm trying to say is, in a sense, you could do a lot of things with reflection, but I think that this concept of heterogeneous generators is important enough for us to consider to have an extension. And I definitely can see how people are going to gain from having our algorithms.
Yeah.
So maybe, not tomorrow, but maybe like for 29 we can talk about this.
Well, I could write this. It would be so much better if I didn't have to.
But like certainly like
I love the concept.
Like the first step is definitely to just have for each while. And then once we have for each while, maybe at some point we can say like, hey, so what if we support stuff that only has for each while and doesn't have iterators, and then like slowly build up.
So it's not a range, but you can do most of the things.
Yeah, you can iterate over it. Well, not iterate. Yeah, the terminology is kind of awkward. Like, you can loop over it.
Right. I can do the things I want.
Yeah.
But it's not a pair of iterators logically based.
Yeah.
We
And
can definitely go in the path of ranges and do like a incremental.
Like it's not a breaking change.
Yeah.
Like it's a pure extension. It's just a wild extension. Yeah.
So, can you go back to the slides? What needs to be done?
Mm-hmm.
This one. So, you're saying that it needs to be done, but you're also saying like proposals are welcome. So, does it mean that you are not doing that?
So it would go quicker if other people would also help, with doing that.
Yeah. What? I mean, except fixing for infinite range, what do you consider the most important? I mean, the top priority.
The top priority, I consider the for each while customization part.
Okay. And the next question then is, I mean, I understand it's kind of my job, but do you have any idea how for each while influences parallel?
So the way it implements is probably not parallelizable, since you can't split it into chunks.
Yeah, but you also said it's a kind of hidden optimization.
Yeah, it's a hidden optimization if you don't need to split, it's for the serial case. Okay. Because the serial copy is just a range-based for loop. It's just a for loop. Okay. And this can be turned into a call to for each while.
So, in other words, does it have, let me put my question differently.
Sure.
Does it have any effect on the random access iterators?
No.
Okay.
I mean, maybe. So like I think concat view is random access.
Yes.
It's just slow random access. And if you call it before each while, it's faster. But the problem is, what you're doing in the parallel algorithms is you're like taking the random access range and you're splitting it into chunks. And then you're having a loop over each chunk. And making that recognize, I'm a chunk of a concat view. So I can this slice can be done with the appropriately nested loops. That's non-trivial to recover that information. So you can't really benefit from that unless there's some way to for each while of a subrange of two iterators identifies the range it's from, and then it knows, okay, so I can do the loops,
Okay, yeah.
Yeah.
Okay. I mean, evaluate it more in details in the future, but I understand your initial impression.
Yeah. So the initial impression is that it's not helpful for the parallel algorithms. It might be at some point in the future, but not right now.
Great job.